All right, we're looking at Module 7, Lesson 3. We just spent a whole lot of time learning how to draw covalent compounds, and I spent so much time on that because it's necessary in order to do other things like today's lesson and Lesson 4, so it's critical that we have that foundation. Today we're going to be looking at bonding theories, which has a lot to do about the shapes of molecular compounds. What we have learned about thus far has simply been learning the structural formulas or the Lewis formulas. And all those do is those just simply show us the kinds of elements and how many atoms of each element are in a compound. It doesn't tell us anything about how it's put together or what it would look like three-dimensionally. The first thing that we're going to look at today is molecular orbitals. Now, we learned about orbitals back in Module 4 when we learned about the electron, and we learned that orbitals are the regions of space where you have electrons. You had 4 different sublevels, the S, the P, the D, and the F, and they each had a different number of orbitals. So a molecular orbit, like an atomic orbital, is just the orbitals in an atom. So a molecular orbital are the orbitals in a molecule. They're very similar. 2 electrons can still take up residence there, but most of the time it's electrons that are coming from 2 different elements because they are bonding. So these are bonding orbitals. And so I have just an image over here, like if this is a hydrogen and here's a hydrogen and we scooch them together so that they overlap, this would be showing you where you have the hydrogen electron from the left and the electron from the right. When they get together, they make this new region of space, which is called a bonding orbital. There's 2 different types of bonding orbitals that we can have. There's one called sigma and there's one called pi. So let's look at sigma first. Excuse me. Sigma bonds are where you have 2 atomic orbitals that overlap and they are symmetrical around the axis that connects them. There are 3 ways to have this. You could have 2 s orbitals like these. So 2 of the spherical orbitals that overlap, they will make a sigma bond. You could have 2 p orbitals. Remember, p was dumbbell shaped. I said it was kind of like an infinity symbol. If you laid them on their sides horizontally and overlap them end to end where the purple comes together, you get this is a sigma bond right here. You get a sigma bond. If either one of these, if you drew a straight line through them, this would be called the bonding axis. And if you could take that axis and you could spin it around, you would see the same thing the whole time that you were spinning it around. Nothing would ever look any different. It would be symmetrical all the way around that axis. Same thing for this one. If you took it and you spun it, you would never see anything any different. It would always look the same as you rotated it, as you took it and spun it this way. Or likewise if you spun it the other direction. Either way, you're going to see the same thing the whole time. The other thing that you could have that I couldn't find a good picture of was if you had an S and a P. So if you took one of these spherical S orbitals and you overlapped it with a P orbital like this, if you put these 2 together, you would get another sigma bond. Sigma bonds are strong, and this should be the lowercase. I forgot to go through. This is in all caps, and the capital looks slightly different. So if you had pi bonds, which this is the lowercase version, what you're used to seeing for pi, sigma bonds are stronger than pi bonds. Let's look at pi bonds for a second. Pi bonds are where you have 2 p orbitals that overlap again, but this time instead of laying them down on their sides like we did before, they're standing up. They're vertical. They're overlapping side by side. And when they do this, they make something that is not symmetrical around the axis. Right here's the axis that's already drawn. And as you can see, if you spun this around, like if you spun it into the screen, part of the time you would see this area of space, and part of the time you would see what we're seeing now, you'd see nothing. It is not the same the whole way around. So these are called pi bonds. They are weaker than sigma bonds. So what do I want you to know at this point for test material? I want you to know the definitions of sigma and pi bonds, and I want you to understand what can make them and their strength. And then I want you to know this. This is what it all boils down to. All single bonds are sigma bonds. And if you have double and triple bonds are always 1 sigma and the rest pi. So let's take this for example. If I gave you CH4 and I ask you for how many sigma and how many pi bonds were in this, what I would want you to be able to do is draw out the structural formula or the Lewis structure. And then I would want you to go, well, it has 4 single bonds, and I know that single bonds are sigma bonds. So this has 4 sigma bonds and no pi. Okay, what if it was something like this? What if it was carbon dioxide? I would want you to be able to draw that out and look at it and go, well, she said that double bonds are 1 sigma and the rest are pi. So that'd be 1 sigma, 1 pi on that side. That'd be sigma and that'd be pi. So it's got 2 sigma bonds and it's got 2 pi bonds. If you had a triple bond for whatever reason, like nitrogen bonded to itself, then that would be 1 sigma, and these other 2 would be pi and pi, because our rule is that double and triple are 1 sigma and the rest pi. So this one has 1 sigma and 2 pi, okay? It goes further than this. If you go into a college level chemistry course, we can get into like more than just this. You know, there's a lot more to it. We're just kind of scratching the surface a little bit. Okay, other than this, other than looking at sigma and pi bonds, we really need to look at VSEPR theory. VSEPR theory is VSEPR theory. It stands for the valence shell electron pair repulsion theory. That's where we come up with VSEPR theory, but I pronounce it VSEPR. It's what I was taught. Valence shell electron pair repulsion theory says just that. It says that the electron pairs that are in the valence shell are going to repel each other, because remember, electrons are negative and opposites attract, like charges, they repel. Electrons repel electrons. So when you put them around an atom, like a central atom, so if we put electron pairs around this, remember there's electron pairs in each of these single lines because they're single bonds, they are going to want to push each other far enough away that they're as far away as they could possibly be from one another. It's going to help us predict shapes, and the only way that you can do VSEPR shapes is if you can draw the Lewis structures or the structural formulas, one or the other. This is a common question on the NC final exams, for them to just give you something and say, like, you know, which of these is tetrahedral, and then you have to look at all of them and decide, but the only way to decide is to draw them out. You must do this. So here is how this is how I present this to my students. It's not how you're traditionally going to find it in a textbook. But you can memorize this way. There are going to be 5 basic shapes that we're going to memorize, and they're based on the number of attached atoms that you have on your central atom. So if you have 4 attached atoms to a central atom, there is only one possible shape that you could have, and it is called tetrahedral. Okay, so here is an example of that. If we take something like CH4 and we draw it out, okay? I know by looking at just the formula that this has 4 attached atoms. I see the 4, and I know from my drawing experience that C has to go in the middle. And I'm going to draw this 3-dimensionally. So here's my C that would go in the middle. What happens from there is that you would end up with 4 H's. 3 of them would come down. I did it. Oh, I'm talking and writing and it doesn't work out well. You would have your H's that would come down here. 3 of them would come down to the bottom, kind of like a tripod. And the way that this is often drawn is like using kind of triangle shapes to show that these come out at you, like they're crawling out at the screen, coming at your face, and a dotted line for this one to show that it's going back, like it would be going back through your computer screen, and then one that goes up in the air. I don't know if you can picture that whatsoever. You know, we could draw it out like here's your H right here, here's an H right here, this one's going back in space, and this one's going up top, okay? Doing this with bullet, I usually do it in class with styrofoam balls and toothpicks. I might decide to do some of that on a camera for you guys with like a molecular set so that you can kind of see it. So stay tuned and we'll see if I can make you a 3D video. Okay, there's only one shape. You could memorize 4 attached atoms. It has to be tetrahedral. Now, if you have 3 attached atoms, there are 2 possibilities. possibility number 1 is called pyramidal, and possibility number 2 is called triangular planar. Okay, for pyramidal, so here's one shape and here's the other one. For pyramidal, what you end up having is it's this basic shape right here. It's tetrahedral, but we're going to take one of these off. So if we take one of these off, what'll have to be up top is a pair of electrons. It's the only thing to push these 3 down. So a good example of this would be, let me see, PCl3. So if we draw out PCl3 like we've been doing, you're going to have to look at this. PCl3 would have this Lewis structure. There's the P, and it would have 3 Cl's around it. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And hopefully you can see these dots. I'm not wanting to take a lot of time. 4, 5, 6. So here's the Lewis structure of PCl3. What I am concerned about is I'm concerned about the phosphorus right here. I'm looking at these in the green box. Okay, I could care less about the chlorines. I see them there. I know that I have 3 attached atoms, so it either has to be a pyramid or triangular planar. But I'm concerned about the number of unshared pairs. You see this unshared pair up here? What it's going to do is it is going to be like this one, except it's going to take up its own region of space up here. So instead of seeing this H, you're simply going to see nothing. So what it's going to do, I wonder if it'll just erase the green. Yeah, there we go. What it's going to do is it's going to put the P in the middle. Oops, let me do this 3-dimensionally. So you're going to see the P right here in blue. You're going to see the blue dot. And then you are going to see the reds. They're still going to come down and to the front. There would be a chlorine. You would have another chlorine coming down here. You would have another chlorine going to the back. And then up here, you would see nothing. It is going to be down kind of like a tripod, and I didn't make it look like it goes all that much down. It's going to be kind of like a tripod because you have an unshared pair of electrons that is forcing that chlorine down to the bottom. So up here, there's a region of space. Now, we can draw them in there. I mean, I could put the electron pair up here. Like, they're going to live in this little space up here, but you don't see them. You see this bottom section, so you'll see a pyramid. Now, what if it was something different like BF3? We looked at this. The Lewis structure of BF3, or the structural formula, is simply this. There are 3 fluorines attached. The deal this time that makes it different from this one is there's no unshared pair. I have 3 atoms attached, and I do not have this unshared pair. So what we would have is we would have a boron in the middle, and then we would have a fluorine, and we would have another fluorine, and we would have another fluorine. They would all be in a flat plane. There would be no pyramid to it. They would lay straight down on your tabletop, or you could stick all of them up against a wall and they would all touch it. So they make up, that's where the planar comes in. They all fit in the same plane. These do not. If we stood these up on my table, if I put a table up underneath this, it would stand up off of the tabletop, and this would stick up in the air like a tripod. This one would lay down flat on my tabletop. So it's a pyramid if you have an unshared pair of electrons, and it's a triangular planar if you have no unshared pair. Both of these have 3 attached atoms. Our last category is if you have 2 attached atoms. Oops. Okay. So similarly, you would have something that is bent, and then you could have something that is called linear. My pen has decided to slow down here on me. So as far as bent goes, it's another version of this tetrahedral shape. It's got this idea of 4 regions of space, but this time what's going to happen is we're going to have electrons in one region, like right here, and then we could have electrons like right here in this region. So you don't see these electron regions, you only see the bottom 2. So it looks bent, kind of like a boomerang. So an example of this, and I'll erase it back off of my original drawing, an example of this would be, H2S. If you draw out the Lewis structure for H2S, or the structural formula, you will get this. You will get 2 attached atoms, but you have 2 unshared pairs of electrons. What that means is that these can't lay in a straight line. They're going to have to be a version of this. So you'll see the S in the middle, and then you'll see the 2 H's attached to it, like this. And then that's all you see. You will see something that is bent, because on this you have 2 electrons in one region and you'll have 2 electrons in another region. You just don't see the electron space. You only see this. So you will call it bent. All right, if it's linear, then it doesn't have these unshared pairs of electrons. For example, CO2 we drew earlier. Okay, CO2 has 2 doubly bonded oxygens on it, and it doesn't matter. Maybe it's a good idea that I do this one as an example. The double bonds make no difference. Double, single, triple, it doesn't matter. We're not looking at whether or not it's double bonds or single bonds or triple bonds. We're just looking at how many attached atoms and does it have any unshared pairs of electrons. It has 2 attached atoms, the O's, but there's nothing. There's nothing else, which means that as far apart as you could possibly get those O's is if you make this thing be a straight line. You would have an O in the 2 O's on each end and the carbon in the middle, and they would not get forced down. This would be a note because there's nothing up here. So they are just simply straight. They make a straight line. Okay. Now, there's all different kinds of ways to do this. I've always just kind of recommended that you do it by kind of common sensing it. You can memorize 4 attached is tetrahedral, 3 attached you have pyramids or triangular planar. Pyramids have an unshared pair, triangular planar do not. And 2 attached, you're either bent or linear. Bent have unshared pairs, linear do not. Okay. I may ask you to draw these for me on our test. It's totally possible that coming up that you could have to draw them in order to give these to me for your test answers. Now, for your practice problems with this, you are looking at this. Let's see if I can make my mouse work. You're looking at this particular part of your worksheet this time. You do not have to print it out again. And all I'm looking for you to do on this is not to do 3D shapes, but to give me VSEPR shapes. VSEPR geometry means tell me, is it tetrahedral? Is it linear? Is it bent? Is it triangular planar? If you just want to give me the words, that would be more than sufficient, okay? That's what you're going to do all the way down the sheet. I don't think this should take us anywhere near as much time as it did beforehand. So from here, go to the practice, ask me if you have questions, and we'll be moving on from here.